Hi there, so we've got the Algebraic Proof exam question solutions. Now there is a pause button there, but you should have been doing these at home anyway, so you shouldn't really need to pause. If you haven't, then do it now, and then unpause when you're done. But otherwise, here's the answers for the work that I got you to do last time. So, prove algebraically that the sum, so that means add, of two consecutive integers is always an odd number. Well, there's one integer, n, and the next one, the consecutive one, would be n plus 1. And it says sum them together. So I'm going to sum them together, and putting those together we get 2n plus 1. Well, we know that the 2n bit is even, because anything, divisible by 2, which this will be, is even. So move it along one, must be an odd number. Job done. Next one, as again, you don't need to pause unless you haven't done it, then pause and unpause. But otherwise, you should just be marking your work. I'm not going to keep saying that. You get the idea, okay? So prove that the sum of three consecutive odd numbers is always a multiple of 3. Well, let's start with one odd number. So that's even. So if I do plus 1, that's odd. Now the next odd number is going to be 2 jumps along, isn't it? Because it'll go even, then odd after that. So 2 more jumps would be plus 3. And 2 more jumps from there would be plus 5. Now I need to add them together because it said sum. So we'll add them all together. And let's do some simplification. 2n plus 2n plus 2n is 6n. 1 plus 3 plus 5 is 9. Now I need to show that this is a multiple of 3. So I'm going to factorize 3 out of these numbers and put it on the outside of a bracket. So 6n divided by 3 is 2n. 9 divided by 3 is 3. This is clearly a multiple of 3. Good. Question 3. Pause if you haven't done it. Otherwise, just keep on going. 3n plus 1 squared take away 3n minus 1 squared is always a multiple of 12 for all positive integer values of n. Okay, so we got the old integer word in there. Well, firstly, let's expand out these two brackets. Now, if I expanded this, if I FOILed it, I would do 3n plus 1 times 3n plus 1, which would get me 9n squared. I'd then have 3n, I'd have another 3n, and then I'd have 1 times 1, which is 1. Okay, so that's that bracket multiplied by itself. And then I'm going to subtract. Well, let's multiply this bracket by itself. And I'll have 3n times 3n will be 9n squared. Then I'll have 2 lots of negative 3n. And then minus n times minus n, or sorry, negative n times negative n is positive 1. Why does it keep saying negative n? I meant negative 1. Anyway, square that, you get positive 1. So we've expanded both sets of brackets out. Now I've put them in brackets because I'm taking one away from the other, which means, well, the first bracket will just be as it is. That's all fine, it's all positive, it's all happy. Then I'm going to subtract this bracket, which means I'm subtracting 9n squared. Well, that's straightforward. Then I'm subtracting negative 3n. Well, if I'm taking away a negative, that becomes a positive. And then I'm going to subtract another negative, so that's a positive. So that will be also 3n, and subtract that positive, minus 1. Okay, what have we got here then? Well, we have got 9n squared take away n's 9n squared. That leaves nothing. I've got 3n plus 3n plus another 3n plus another 3n. That is actually 12n. And then I've got minus 1 on the end. So that's 1, take away 1, leaves nothing. It just occurred to me, oh yeah, and by the way, this is obviously a multiple of 12. So it's a multiple of 12, happy days. You might have, before you subtracted these, actually simplified your brackets a little bit, which would have been sensible. And when I did my notes, I did do that, but I forgot to do it now. But, you still get the same answer. Oops, that's subtract 6n plus 1, which makes this a little bit more obvious because then you're doing 9n squared plus 6n plus 1, take away 9n squared plus 6n, subtract 1. Yeah, and it's all just a little bit more obvious that you end up with 12n, he says, making a right hash of it. But either way, you get to the same answer. All right. Question 4. Pause if you haven't done it. Done. Great. So n is an integer. Prove algebraically that the sum of this and this, so and n plus 1, is always a square number. Right, now I gave you a hint here. A square number could be written as a load of stuff squared. Yeah? So let's just get stuck in, do some expansion, see what happens. Right, n times n is n squared. N times 1 is n. And then I'm going to add that to n and 1. So n plus n is 2n plus 1. Well, that doesn't look very squared to me at the moment. That bit is, but the rest of it isn't. But this is a quadratic expression that can be factorized. Remember, find those factor pairs of the n number. So 1 times 1 makes 1. And that's the only pair. So that's the pair I'm going to use. So this could be written as n plus 1. I'm going to use these two numbers in some double brackets. That's an n. So n plus 1 times n plus 1, which is n plus 1 squared, because the bracket is times itself. All I did, the tricky bit there is noticing this is a quadratic expression you can factorize into double brackets. Yep. Anyway, this is a squared number because it doesn't matter what's in that bracket there, it's squared. Yeah. Number 5. So pause your video if you haven't done it, otherwise let's walk straight on. Prove algebraically that the sum of the squares of any two positive even integers is always a multiple of 4. A lot going on there. So firstly, it says any, and I told you here, hint, because it says any two numbers, you need two different letters. And the squares, let's start with this bit here, the squares of any two even positive integers. Well, let's do two even numbers first of all. The first one we'll just write as 2n. Now the next even number, oh no, sorry, it's not the next one, it's not consecutive, is it? It's any even number. So let's do 2m. So I've got 2n and 2m. Okay, and it says the squares of these. So let's put them in brackets and square them, right? So that's the square of those two even numbers. And it says prove that the sum of these. So we're going to add those two square numbers together. This sort of question is only hard because you really need to decipher what the question's saying and write it out. Anyway, what we're proving is that when we do this and we expand it, it's always a multiple of 4. So let's just do some algebra crunching. Well, 2n squared, so 2n times 2n will be 4n squared. And 2m times 2m will be 4m squared. Put those together. I can factorize those to get 4n squared plus m squared. Now, it doesn't matter what these two integers are, n and m. You can see that it's a multiple of 4 because it's 4 times whatever is in there. Yep, happy days. Right, let's move on then. I've also got you 3 extra questions because that's quite short for a lesson, really. So let's do 3 more. Now, this time you are going to pause it. This is 1 of 3. I promise it's only 3 questions. I want you to try and prove what's there and then unpause when you're done. We've unpaused then. So prove algebraically that the sum, so that means add, of the squares of any two positive integers is always even. So two odd positive integers, right? So let's go for 2n plus 1 because 2n is even plus 1 makes it odd. And it's any two, so let's use a different letter. So 2m plus 1. Now I need to sum the squares of these, so I need to square them and sum them, add them together. Right, let's do that. Some number crunching then. 2n plus 1. Now, I'm not going to write out the full thing for this. If you don't know how to FOIL, how to expand double brackets, then you probably need to go and look that up. I'm just going to write down what the answer is going to be. Now, when I expand this out, I'm going to FOIL it. So I'll have 2n squared plus 2n plus another 2n plus 1 times 1 gives me 1. So that's my first bracket times by itself. And let's do the second one, which will be very similar. We'll have 4m squared plus 2m plus another 2m plus 1 times 1, which is 1. Okay, I say if you don't know how to FOIL or expand double brackets, you need to go look it up. Let's do a little bit of tidying up. So 4n squared plus 4n plus 1, and 4m squared plus 4m plus 1. And what do we need to do? I need to add these together. There's no tricky negatives here, so we can pretty much ignore these brackets and just add stuff together, make it a bit neater. So let's put the squared terms first, because mathematicians, we like having things in order. Then I've got 4n and 4m. None of these things can go together yet because they're all different letters. And then lastly, I've got 1 plus 1, which is 2. Okay, I've done the algebra crunching, but it says that I need to show this as even. Well, things that are even are always multiples of 2. So let's factorize it by taking 2 out of each of these terms. 2n squared plus 2m squared plus 2n plus 2m plus, and when you divide this by 2, you get 1. Look, doesn't matter what's in the bracket, it's times by 2, which makes it even. Job done. Okay, question 2 of 3. Pause. Unpause when you've written it out. Don't just do it in your head, write it down. Be careful with what this is saying. The algebra on this one's tricky. Number 3 is a bit easier, but anyway, I'm going to stop talking. Zip. Mouth is zipped. Go. Unpaused. Cool, so what we got? The sum of the squares of 2 consecutive odd numbers. So we can have 2 consecutive odd numbers, 2n plus 1 and 2n plus 3, is always 2 more than a multiple of 8. Well, we'll come to that in a minute. Let's just do the sum of the squares first. So which means I need to square them. I need to sum them. Again, if you're not sure how to expand double brackets, you need to look it up. But 2n times 2n is 4n squared. You'll then have 2n and another 2n, and 1 times 1, which is 1. And then over here, we'll expand this one. Now, 2n times 2n is 4n squared. Now, when we start doing 2n times by the 3, we get 6n, and then another 6n, and then 3 times 3 is 9. So let's simplify that a little bit. So 4n squared plus 4n plus 1, and 4n squared plus 12n plus 9. And there's no tricky negatives, so we can just go straight ahead and add together and simplify. So 4n squared plus 4n squared is 8n squared. 4n plus 12n is 16n. And 1 plus the 9 is 10. Right, now let's go on to the tricky bit. I need to show that this is 2 more than a multiple of 8. So I need to show it's a multiple of 8. So 8 brackets, something or other. But it's actually 2 more than that. Well, can I do that? Yes, I can. If I rewrite this as 8n squared plus 16n plus, and let's split the 10 into 8 plus 2. Right, there's my plus 2. Now, what I'm going to do, if I get another colour pen down here, I'm going to take this bit of my expression. I'm going to leave the plus 2, that's obvious. I'm going to factorise this, taking 8 out as a factor of each one. So 8n squared divided by 8 just leaves n squared. 16n divided by the 8 leaves 2n. And 8 divided by 8 leaves 1. There we go. This is a multiple of 8, but this makes it 2 more. Yeah. Okay, now the last one is a bit easier than that. It's tricky, that one. Pause the video. I'm not going to say anything. You just do it. Okay, right. Prove that the difference, so we've got a subtraction here, between the squares of any 2 consecutive integers is equal to the sum of these integers. So any 2 consecutive integers. So there's one integer. There's the next one. I need to do the difference between the squares of these. So I need to do the big one, take away the small one. So actually I need to reverse these. I need to do that, subtract that. Now, surely you probably can do this the other way around, but it's a bit neater. If I'm doing it this way, I know this number's bigger than this one. So it's just better, isn't it? It's just big number, take away small number. Okay, n what plus 1 squared. Well, n times n is n squared. N times the 1, so we get 1n and another 1n. 1 times 1 is 1. Take away the n squared. Let's just neaten it up a little bit before do anything else. So n squared plus 2n plus 1. And I'm going to subtract from that n squared. Well, n squared take away n squared will cancel out, leaving 2n plus 1. Right, what did I have to prove though? We have to prove that when we do that, it's equal to the sum, I don't know why I just drew that, that's rubbish, to the sum of these integers. So let's take these integers and add them, and I get 2n plus 1, which is the same as that. Happy days. Okay, well done. Proof can be really tricky because just about every question is different. Just when we spoke in the lesson before this, we spoke about how we got those elements. And as you can see, hopefully by now, that they're pretty much always the same elements. It's just how we use them and how we build them together depends on the wording in the question. So the wording is always key. Yeah. Anyway, well done. We're probably going to move away from proof now. Maybe, unless I'm feeling mean, and then we'll do some more because I really like proof. I really like it. Anyway, right, I'll see you again. Take care. Bye-bye.